discuss about solution of a system of a linear equation by Gauss elimination methods. So, as we know that this one is a direct method. So, in this lecture first we discuss about the theoretical concept of a Gauss elimination methods. Then we solve two numerical example, one using only a Gauss elimination method and second one using the partial pivoting with the help of a Gauss elimination method. So, let us discuss about what are the theoretical aspect of a Gauss elimination method. So, let us take a system of a linear equation having a n unknowns and m equations. So, this one is a general system of a linear equation a11 x1 plus a12 x2 up to a1n xn equal b1. This one is the first system of a linear equation. Second system of a second equation of a system of a linear equation is a a21 x1 plus a22 x2 up to a2n xn equal b2. Similarly, in a similar manner, am1 x1 plus am2 x2 up to amn xn equal bm. So, how many number of unknown in this equation? There are n unknowns x1, x2, x3 up to xn. And how many number of equation? First equation, second equation, third and so on. How many number of equation? There are m equations. So, suppose here we assume that this system of a linear equation have a solution and that solution is a unique solution. This one is an assumption. Now, you may also write this system of a equation in a matrix form. How we write? Just write the coefficient of a x1, x2 up to xn, then this become what? You may write here, write a matrix A, here we write a A11, A12 up to A1m, A1n, similarly A21, A22 up to A2n, and last row with the am1, am2 up to amn. Okay. So, now here we write the unknowns x1, x2 up to xn, this one equal b1, b2 up to bm. So, this one is nothing else matrix equivalent form of this system of a linear equation. This system of a linear equation, suppose this one is a system of a linear equation, here we write a system of a linear equation, system of linear equation. System of linear equation. And this one is a what? This one is a matrix form of a system of a linear equation. Matrix form of a system of a linear equation. Matrix form of system of a linear equation. System of linear equation. Linear equation. System of linear equation. So, obviously, this one is a system of a linear equation means each equation is a linear, means the first equation is a linear, second equation is a linear, third equation is a linear, and all the equation is a linear. So, this one is called system of a linear equation. If we represent the matrix A, means a coefficient of unknowns by the capital A, this one is a matrix A, this one is a column matrix X, and this one is a column matrix B. Then we may write this one equal capital A x equal capital B. So, this one is the equivalent form of this system of a linear equation. If we multiply first row by the column of x, then a11 x1 plus a12 x2 up to a1n xn equal b1. Then we find the first equation of a system of a linear equation. If we multiply the second row by this column, then we find the second row of a system of a linear equation. Now, how we solve this one? By the Gauss elimination method. As it, from its name, there are one term elimination. So, in a Gauss elimination method, there are two steps. In a first step, we perform the elimination known as a forward elimination. Then, to find out the value of an unknown after the elimination, known as a backward substitution. So, in a Gauss elimination method, there are two steps. First one is a forward elimination. So, if we write first step is a forward elimination, forward elimination, forward elimination, elimination, and second step is a backward substitution, backward substitution, substitution, forward elimination and backward substitution. Now, what will happen in a forward elimination? In a first step, if we talk about a forward elimination, forward elimination, forward elimination step, elimination, forward elimination. So, suppose here we started from the matrix form of a system of a linear equation. So, what is the matrix form of a system of a linear equation? Matrix form of a system of a linear equation is a Ax equal capital B, Ax equal B. So, from given system of a linear equation, first we write a matrix form of a system of a linear equation, then we write a augmented matrix, then we write a augmented matrix. What is the augmented matrix? If here we write the expanded form of a matrix form of a system of a linear equation, then this may be written as a what? A11, A12 up to A1n, A21, A22 up to A2n. Similarly, AM1, AM2 up to AMN, and here this one is a x1, x2 up to xn, and this one equal to the what? B1, V2 up to Bm. Once we write a matrix form of a system of a linear equation, then we write a augmented matrix, augmented matrix, augmented matrix, augmented matrix, augmented matrix. So, as we know that what is augmented matrix? Means a partition matrix A then B. This one is augmented matrix. Here we define the augmented matrix like this one, then partition, then we write a matrix B, then we write a matrix B. So, first of all we write a augmented matrix. In a forward elimination method, what is our aim? Our aim is to write a augmented matrix, means a given system of a linear equation in a upper triangular form. In a upper triangular form, what will happen here in upper triangular form? Meaning of upper triangular form is a below the diagonal elements of a matrix A, all the elements become 0. So, what is our aim? Our aim is to convert all the element below the diagonal element equal to 0. This process is called elimination. First we eliminate except the first element of a first column, all the element of a first column equal to 0. Then we repeat this process for the second column, started from the second row, third column started from the third row, and so on. So what is our aim? Our aim is to convert the given system of a linear equation into a upper diagonal form of a system of a linear equation. Upper diagonal form is we try to convert the matrix A into a upper triangular matrix. So what is our aim? Our aim is to convert the matrix A into a upper triangular matrix. Now how we convert the matrix A into a upper triangular matrix? Just we write a expanded form of a augmented matrix. Now how we write a expanded form of a augmented matrix means we write the values of A and values of V. Means we write the values of A and values of B. So now augmented matrix become what? Now augmented matrix become A partition B, and this can be written as, here first we write the matrix A means A11, A12 up to A1n, A21, A22 up to A2n, and last row with the AM1, AM2 up to AMN. Then partition, then we write the values of a matrix B. So this one is a what? This one is a V1, V2 and so on. Mth row there is a M elements. Now what is our aim? Our aim is to convert this matrix into a upper diagonal matrix. Upper diagonal matrix means below the diagonal elements, all elements become 0. This one is a diagonal element. This one is a diagonal element. This one is a diagonal element of a matrix A. Now what is our aim? Our aim is to convert these element, eliminate the coefficient of these element. So how we eliminate means we try to convert the values of these element, these coefficient equal to 0. So for this one, first stage of elimination, in a first stage of elimination, we eliminate all the element of a first column except the first elements. Means we convert the A21 equal to 0, we convert the A31 equal to 0, we convert the AM1 equal to 0 in a first stage of a elimination with the help of a first row. So how we convert this one? So here we perform what? Here we perform a row operation on a second row, third row and mth row with the help of only first row. So here with the help of a first row, this element is known as a pivot element. With the help of this element and this row means a common element between first row and first column is known as a pivot element. So first we choose the pivot element. How we choose the pivot element? The element of a first row and first column is a pivot element. Here pivot element is a what? A11. So what is the necessary condition to apply a Gauss elimination method? Pivot element must be does not equal to 0. If this one equal to 0, then you cannot apply the Gauss elimination method. So what will happen? Pivot element, first we choose the pivot element A11 and this must be does not equal to 0. So, if this one equal to 0, then we perform the partial pivoting and complete pivoting. Later on we discuss about what is the partial pivoting and complete pivoting in case if pivot element does not equal to 0. Equal to 0, not equal to 0, then if this one is not equal to 0, then we able to perform the first stage of elimination. So, once we ensure that A11 does not equal to 0, here we assume that A11 does not equal to 0, then we perform the following operation to convert the A21, A31 up to AM1 equal to 0. In a second row, we perform this operation. R2 tends to what? R2 minus, with the help of a first one, R2, we try to convert this element equal to 0. A21 divided by A11 R1. Then what will happen here? Try to observe this one. Try to concentrate on this operation. R2 tends to R2 minus A21 divided by A11 R1. Means first we divide the first row by the A11. If we divide the first row by the A11, then pivot element become 1. If the pivot element become 1, means A11 become 1, then we multiplied by the A21. If we multiplied by A21 in a 1, then this become A21. So, if we perform this operation R2 minus A21 upon A11 R1, then this element become 0. Means of in a first column, second element become 0. Similarly, if we perform this operation R3 tends to what? R3 minus multiplied by A31. A31 divided by A11 R1. Then we able to convert the third element of a first row equal to 0. Similarly, in continuation of this, in a mth row, we perform what? We perform Rm tends to Rm minus AM1 upon A11 R1. If we perform these row operation in a first stage of elimination, then we able to convert all the elements except the first element of a first column equal to 0. Now, after first stage of elimination, suppose what is the reduced form of augmented matrix, means after performing these operation, these row operation, there is a change in this element and V2 and this element and all the element will be changed. So, after performing the first stage of elimination, suppose the reduced augmented matrix be like this one, reduced augmented matrix, reduced augmented matrix. Now, what will happen in a reduced augmented matrix? There is no change in a first row, A11, A12 up to A1n, and partition B1. There is no change in a first row. There is a change in a second row, and all the element of a first column become 0. Suppose there is a change in a second row of a second column. Suppose this, after changing, this become A22 prime, A22 dash, single dash. Similarly, A2n dash and V2 dash. After performing this row operation, means the first row operation, R2 tends to R2 minus A21 upon A11 R1. We perform the operation on R2. So there is a change in the values of a coefficient of a A22, A23 up to A2n and Bn. And after modification of the value, suppose this one is a value A22 dash, A2n dash up to B2 dash. Similarly, in a third row, for sake of a simplicity, suppose here we write the third row also. So this become what? A32 dash up to A3n dash, and this one become V3 dash. In a similar manner, suppose this one is a what? This one is a AM2 dash up to AMN dash, and next one become BM dash. Now we perform the second stage of elimination. In a reduced augmented matrix. Second stage of elimination. Second stage of elimination. Second stage of elimination. So for the second stage of elimination, which one is a pivot element? First we examine the pivot element. So second stage of element, which one is a pivot element? Second row and second column. Common element of a second row and second column. So this one is a second column and this one is a second row, and which one is a common element? A22 dash. So pivot element become what? Pivot element become A22 dash. Here also in each stage of elimination, it must be necessary to apply a Gauss elimination method. Pivot element does not equal to 0. If any stage of elimination pivot element equal to 0, then either we perform a partial pivoting or complete pivoting to ensure that the pivot element does not equal to 0. If we unable to ensure that pivot element does not equal to 0, then we unable to apply the Gauss elimination method. Here we assume that this one does not equal to 0. Then we perform the second stage of elimination. With the help of a second row, we try to convert the third row, fourth row and mth row, element of a third row, fourth row up to mth row equal to 0. Means a element of a second column except the first and second column, all element equal to 0. We try to convert the all element of a second column except first and second element equal to 0. So for this one, we perform what? We perform the row operation in a third, fourth, fifth up to mth row. So here we perform the R3 tends to what? R3 minus A32 dash upon A22 dash R2. Means in a reduced augmented matrix, first we divide the second row by the A22 dash, then pivot element converted into a 1, then we multiplied by the coefficient of a dash 32, then the augmented matrix become coefficient of augmented matrix means a pivot element become A32 dash. When we subtract the third row by the multiplication of a A32 dash upon A22 dash R2, then this element become 0. In a similar manner, we perform the row operation on a fourth row, and this one is a R4 minus what? Minus A42 dash upon A22 dash R2. with the help of a R2. In a similar manner, here we write in a similar manner, in a Rm mth row, Rm tends to what? Rm, what we write in a previous stage? This one, Rm minus AM2, A dash M2 upon A22 dash R2. So, with the help of these row operation, we able to convert the A dash 32 means all the element of a second column except the first and second element, all the element converted into a 0. Then again we write a what? Again we write a reduced augmented matrix. Now again reduced augmented matrix, reduced augmented matrix after second stage of elimination. After second stage of elimination. Suppose the augmented matrix is a what? Augmented matrix is a, there is a no change in a first row, A11, A12 up to A1n, partition, there is a B1. Again there is a no change in a second row of our reduced augmented matrix after stage 1. So, this one is a 0, this one is a A22 dash, and here A2n dash, this one is a B1 dash. But third row onward will change after second stage of elimination, means this value A32 dash with the change, A3n dash also change, V3 dash also change. So, after second stage of elimination, we write this one is a what? We write in a third stage means A32, this one becomes 0, this one becomes A3n dash, double dash. So, here this becomes 0, 0 and so on, this one is a 0, this one becomes 0, 0 and so on, this one is a 0. Now, next element is a what? Next element is a A33 double dash up to A3n double dash up to a V3 double dash. Okay. Now, similarly, there is a change in a fourth row also. Mth row, there is a change, means here we write AM3 double dash up to AMN double dash, and this one is a BM double dash. Here this prime means represent the dash, represent the there is a number of changes. You know, 1 prime means 1 dash means there is a 1 time change in a B. 2 prime or 2 dash means there are change in the value of original value of a V in a 2 times. Means 3 dash BM dash triple dash, meaning of this one is the original value of a BM will change 3 times. So, here BM double dash, meaning of this one is the original value of a BM will change 2 times. So, if we proceed in this manner, what will happen? After first stage of elimination, the first column look like means be able to convert into a what? Upper triangular matrix, first column of a reduced augmented matrix. Now, if we repeat this process up to a what? How many times? N times, means for the first column, for the second column, for the third column, and last one automatically converted. There is no need to convert the repeat the process n time. Why? Because after n minus 1 time only this element will remain. Only this element will remain with prime what? N minus 1 time. So, after repeating this process n minus 1 time, the reduced augmented matrix become what? The reduced augmented matrix, here we write the reduced augmented matrix, reduced augmented matrix reduced augmented matrix after n minus 1 stage of elimination. Elimination means we perform this process n minus 1 time. Then what is the augmented matrix? Reduced augmented matrix. Now reduced augmented matrix become what? There is no change in a first row, A11, A12, A13 up to A1m partitions. This one is a B1. In a second row, there is this one is a 0 and this one is a change 1 time, A22 dash, A23 dash up to A2m dash, this one change 1 time, and third row change 2 times, 0 0, this one become A33 double dash up to A3m double dash, V3 double dash. Similarly, last row changes how many times? N minus 1 time. So, here we write AMN, how many times original value will change? N minus 1 time. So, this one is a VM, this one also change N minus 1 time. Now we able to convert the augmented matrix into a upper triangular form of a system of a linear equation, or you may say also upper triangular matrix. We able to convert the matrix A into a upper triangular matrix, then obviously the corresponding system of a linear equation converted into a upper triangular form. Now we write a original form of a system of a linear equation with this upper triangular matrix of augmented matrix. So, here we write what? Here we write like this one. First we write a upper triangular matrix A11, A12, A13 up to A1m and 0 0 up to 0. This one is a A22 dash, A23 dash up to A2m dash and 0, A33 double dash up to A3m double dash, and last row be the 0 0, and this one is a BMN, AMN, not BMN, AMN. How many times this value, original value will change? N minus 1 time. So, here we write a original unknown coefficient, unknown variables x1, x2 up to xn. Then this one equal to the what? B1, B1 dash, B2 double dash up to Bm n minus 1 dash. Now, this one is a completion of a first step, forward elimination. Why this one is called forward elimination? first we eliminate the coefficient of x1, then we eliminate the coefficient of x2 from the third except the first and second equation, third onward. Then we eliminate the coefficient of x3, then we eliminate the coefficient of xn minus 1 in a n minus 1th stage. Due to this reason, this one is called forward elimination. First we eliminate the coefficient of x1 except the first equation, then we eliminate x2 except the first and second equation, then we eliminate the x3 except the first, second and third equation. Due to this reason, this one is called forward elimination. First we eliminate the x1, then we eliminate the x2, then we eliminate the x3. Successively the value of unknown we eliminate the values of unknown. Due to this reason, this one is called forward elimination. Now after this one, there is a backward substitution. Then what will happen here? If we write a system of a linear equation with this matrix form of a reduced matrix form of system of a linear equation, then what is the linear system of a linear equation? So reduced means reduce, you may also write here upper triangular form, upper triangular form of a matrix, upper triangular form of a system of equation, upper triangular form, reduced system of a equation, reduced form of a system of equation, not a form. Here we write a form, reduced form of a system of equation, form of a system of equation, system of equation. Now what is the reduced form? Here this become A11, just multiplied row by column. We multiply first row by the x1, x2 up to xn. Second row, column of a x, capital X means this one is a dash, this one is a x, this one is a b dash. So first row of a dash multiplied by the x equal to v1, second row of a dash multiplied by the x equal to the v2 dash. So a11 x1 plus a12 x2 up to a1n xn equal b1. Second equation become 0 x1 plus a22 dash x2 up to a2n dash xn equal b2 dash, and third equation become 0 x1 plus 0 x2 plus a23 double dash x3 up to a3n double dash xn equal v3 double dash. Similarly, what is the mth equation? Mth equation becomes 0 x1 plus 0 x2 up to what? Up to a mn n minus 1 at time, original value will change, xn equal bm n minus 1. Now we perform the second step, backward substitution. Backward substitution. So if we closely observe this system of a linear equation, if we try to solve a last one, so all other coefficient except the xn equal to what? 0. Then with the help of a last equation, means if this one is a first equation, this one is a second equation, this one is a third equation, and this one is a mth equation. Then with the help of a mth equation we able to find out the value of a xn, because there is a only one unknown whose coefficient is non-zero. All other coefficient equal to 0 means the coefficient of x1 with the 0, coefficient of x2 with the 0, coefficient of x3 with the 0, coefficient of xn minus 1 is also equal to 0. Then we able to find out by solving the mth equation, we able to find out the value of a xn. We able to find out the value of a xn. How we find the value of xn? By solving this equation, we able to find out the value of a xn. Xn equal bm n minus 1. Bm n minus 1 means the bm value will change n minus 1 time of its original value. Bm minus 1 and this one is a amn n minus 1. Once we able to find out the value of a xn, then look the equation of a m minus 1, m minus 1th equation. Here suppose we write a m minus 1th equation, then this one is a 0x1 plus 0x2 up to one term with a m minus 1 n minus 1 xn minus 1 plus a m minus 1 n xn equal to b m minus 1. How many number of changes? There is a n minus 2 time change. This one is a n minus 2 time change. This one also change n minus 2 times. So here if we closely observe the equation m minus 1, how many number of unknown whose coefficient does not equal to 0? There are two unknowns whose coefficient does not equal to 0. And what is the equation? Equation become what? A m minus 1 n minus 1, how many time it will change? N minus 2 time xn minus 1 plus a m minus 1 n n minus 2 xn equal to what? Vm n minus 2. In a first step of a backward substitution, we able to find out the value of a xn. Now we put the value of a xn here. In a second step of a backward substitution, then we able to find out there is a one unknown only, xn minus 1. Then we able to find out the value of a xn minus 1, xn minus 1. So in a backward substitution, with the help of a last equation means mth equation, we find the value of a xn. Then with the help of a second last equation, using the value of a xn, we find the value of a xn minus 1, and we repeat this procedure. Means in a first step we find the value of a xn. In a second step, using the value of a xn, we find the value of a xn minus 1. In a third step, using the value of a xn and xn minus 1, we find the value of a xn minus 2. Similarly, in our first step we find the value of n, second step n minus 1, then in a 1th value means n minus what? N minus 1th step means n minus 1th step. N minus 1th step means we find what? We find the value of what? We find the value of x1. So why this one is called backward substitution? Because in a first step we find the value of xn, then we find the value of xn minus 1, then we find the value of xn minus 2, and last one we find the value of x1. So due to this reason, this one is called backward substitution. So this one is a theoretical concept of a Gauss elimination method. Once we summarize the Gauss elimination method, what will happen in a Gauss elimination method? First of all, we write the given system of a linear equation into a matrix form. Then from the matrix form of a system of a linear equation, we write a augmented matrix. Then in an augmented matrix, we choose the first pivot element. What is the first pivot element? The common element of a first row and first column, and we ensure that the pivot element does not equal to 0, and here we assume that suppose pivot element does not equal to 0, then we perform some row operations to convert all the element of a first column except the first element equal to 0, means we eliminate the coefficient of a x1 from all other equation except the first equation, and we repeat this process n minus 1 time to convert the given system of a linear equation into a upper triangular form of a system of a linear equation. Once we convert the given system of a linear equation into a upper triangular form of a system of a linear equation, then we perform the backward substitution. In a backward substitution, we started from the last equation. In the last equation, if a given system of a linear equation in a upper triangular form, then in a last equation there is a one unknown and the coefficient of all other unknown equal to 0 except the nth unknowns xn. The coefficient of xn does not equal to 0. Then we find the value of xn. Once we find the value of xn, then we put the value of xn in a second last equation, means m minus 1th equation. Then we find the value of xn minus 1, and we repeat this process n minus 1 time, then we able to find out a value of xn, xn minus 1, xn minus 2, xn minus 3 up to x1. This one is called backward because first we find the last unknown whose subscript is the n. Then we find the n minus 1, means we move back n to n minus 1, then n minus 3, then n minus 4, then 1. Due to this reason, this one is called backward substitution. In a forward elimination, first we eliminate the coefficient of x1, then we eliminate the coefficient of x2, x3, x4. So, due to this reason, this one is called forward elimination.